I was supposed to be at a conference today in Taipei, but Terry, I thought you're not going to come today.
I just fixed.
Okay. Oh, because you like the class, you came? What do you mean, no? Okay, but okay, I skipped the conference for the first day, so I'm here to teach. Okay, so let's get started. So last time we talked about the inflation and how it solves the 4 problems of the Big Bang, right? Do you remember what are the 4 problems of the Big Bang? First one?
Problem of flatness, problem of having dipole,
Monopole. All right.
yes. And
Horizon?
yes, horizon problem and sorry, I forgot.
Okay, 3. Here's help.
I only remember those two. Monopole and horizon.
Oh, Dora, you're very good, right?
No.
Okay. Sorry, what's your name? I forgot to bring a seat. You're Eric, right? Eric, right?
No, Vida.
Oh, Bidan, yeah. Bidan, do you remember?
I think I passed.
You pass? Okay, Jeremy.
Initial transition problem?
Yes, initial density fluctuation, right? So initial density fluctuation, and then flatness, and then horizon problem, and then monopole problem, and inflation can explain them all, right? So that's why we needed inflation, right? Then, okay, we are going to continue to look at the inflation prediction in this chapter. So that last one, as Jeremy said, inflation predicts clumpiness of CMB because there was a quantum fluctuation, and then Hawking radiation is going to create the quantum fluctuation in the CMB, right, in the universe, right? So if there's a clumpiness at very small or large scales, then it's nice to use a Fourier transformation to investigate these fluctuations at different scales, right? Fourier transformation can separate scales, right? Small scale, large scale. So it's convenient. And we're going to look at it, how they do it, how to do it a little bit in general. So in cosmology, very often we use a power spectrum, because we look at small scale, large scale, at different scales. So let's look at it, how people do it. So the low bar is average density of matter, and then delta low is deviation, and then delta low over low bar is a fractional over density, often written by this delta. Right, so this is large, it's over density, this is small, it's under density. Maybe I should close this, it's fine. Okay, then say if large L is a length in one-dimensional universe, then density fluctuation delta is delta rho divided by rho, so then we can expand this in Fourier like this. Maybe I should close this in Fourier series. So C is coefficient at different scales, and then this is Fourier expansion, right? And then K here, Kn here, is the wave number corresponding to different scales, and then this C coefficient is something like this. And then this CKN is going to tell you, how much structure is there at that particular scale. So if there's a lot of structure at large scale, then C is large at large scale. If there's not much structure at small scale, C is low at small scale. So this n corresponds to different spatial scales, large scale, small scale, blah, blah, blah. Okay. So this is just one dimension, right? And then, are you familiar with this kind of thing? These often you use it in different physics field too, right? Okay, it's the same thing. Yeah, it's not particularly special for cosmology. And then we can easily do it in 3 dimensions. To do 3 dimensions, it's super easy. This k, you just put one more line here, then it's 3 dimensions, right? It means vector, right? So in 3 dimensions, it's 1 dimension, it was scalar, but now it's vector, right? So when you put extra line here, then it means it's a vector, kx, ky, kz. So it's 3 components. And then corresponding to this r, it's also vector, okay? And then it's the same thing, right? Same thing. And then this L, this is cubic because now it's a volume, 3 dimension. So, and then, well, it's the same thing, Fourier series. And then what we are interested is this, how much variation in this Fourier coefficient of this delta k here. Yeah, so delta k is at different k, different scales, tell us how much structure there is. What did I say? If delta x is isotropic, then ck or delta k doesn't depend on direction k. So often we have cosmological principle that in the universe at very large scale, in this way and in this way, it's the same, right? Structure is the same in the universe. Then this ck or delta k doesn't depend on direction. So actually we can just look at the radial direction. The universe in this way, universe in that way, is similar at very large scale. That means isotropic. Well, this is an assumption, but then, at first we look at observations, it's true. So, okay, then let's go. Move on. So then what we want to look at is this ck or delta k as a function of wave number or scale, small scale, large scale. So that is called something called power spectrum. So power spectrum we often write down pk, which is delta k average, square average. And this pk is something we look at cosmology very often. So in the present day universe, if the density is, average density is overdense, higher, then because of the gravity, density increases because of the gravity. So for example, in galaxy cluster, we have is a high overdensity region, right? And then because gravity there is larger, so things keep falling into galaxy cluster. On the other hand, if delta x is less than 0, which is lower density, such as voids, then there's less gravity, so things, relatively tend to, move out. It doesn't move out. I mean, it's not pushing. A void is not pushing things out, but then the gravity in other places is larger, so objects tend to move to other places where gravity is stronger. Okay. Yeah, and then in a linear regime, if we just only think about the gravity, then density is going to evolve from self-gravity, so that Fourier modes evolve independently. That means linear. Then power spectrum is very convenient in cosmology. So we write power spectrum, right? Which one is good? So okay, maybe this one. So we write down density fluctuations in terms of, we do a Fourier series, right? And then in a linear regime, this C is going to evolve independently when we only think about gravity. So small scale and then middle scale, large scale, it just independently evolve this parameter. So it doesn't, that if large scale C changes, that doesn't affect small scale in a linear region if we just think about gravity. So this is why it's very convenient to make it a Fourier series. Then you can just look at the individual scale, right? You don't have to worry about correlation between different scales very much. Non-linear scale, it's not the same. Like if you have I don't know, your favorite, you guys like AGN, right? If you have AGN feedback or star formation or galactic wind, then that's not linear. This is going to affect different scales. But if we just look at the very large scale, where gravity is dominant force, it's linear, so it's very convenient in cosmology. So that's another reason people use power spectra in cosmology. I'm going to show where we are going to look. Don't worry about it. Okay, Tomo, we haven't seen any power spectrum yet, but we're going to see a lot of them this next chapter. So don't worry about it. Okay. So that blue line we talked about. During the inflation, self-gravity can be also neglected because inflation is so much stronger than the gravity, right? So then gravitational potential from inflation is invariant under time translation. So that means when after a little bit time after, universe looks the same. So that means, okay, here's a universe, right? And then delta T later universe is a little bit larger, right? But then structure there it looks similar because structure is same, right? In a very short time. So then there must be constant level of fluctuation. So that if the universe gets a little bit larger and then looks similar, then fluctuation should be also similar, right? Then continuous time invariant process in which quantum fluctuations created and inflate out. So there will be no characteristic length scale in the universe. So this, our universe, inflation predicts our universe is fractal. You know fractal? It's this kind of thing. I see, so this kind of thing. Can I play this? Or maybe I need to click it? Yeah, so can online people see this? If online people cannot see it, let me know. Are you online?
Yeah.
Okay. Are you the only online people? Is there online people? Can you see it other than Dora? Are you awake? Are you sleeping?
No.
Okay. Let me share it. Can you see it now?
Yes.
Okay, thank you very much. So this is fractal, right? Fractal structure is something that you see a structure and then you magnify it, zoom in, and then you see the same thing. You zoom in and then you see the same thing, right? So this spiral structure, you zoom in and then you see the same structure again. Zoom in and you see the same structure again. That's a fractal. Our universe is like this. Large scale, small scale, always quantum fluctuation. 100 megaparsec, 10 megaparsec, 1 megaparsec, all quantum fluctuation. It's the same. So that's what means the universe is fractal. Why is that? Because of what I just said, but more intuitively, this. So, okay, let's focus on this. Okay. So, this is a beautiful drawing of expansion of the universe. Say universe at the beginning, it was very small, right? And then there is a Hawking radiation. So this is supposed to be a particle horizon, right? And then there is a Hawking radiation, in this scale to inside of the universe, right? Okay. So the fluctuation around here is going to be quantum fluctuation, Gaussian, right? And then a moment later, universe expands and it gets bigger, right? And then horizon also gets bigger, right? Then in this case, this bigger horizon also create Hawking radiation, right? Create a fluctuation, which is Gaussian again. It's quantum fluctuation. And then this, again, it gets a little bit larger, right? A moment later. And then create at that scale quantum fluctuation. So any scale, because universe as it expands, horizon expands, and then keeps producing Gaussian fluctuation. So at any scale, small scale or large scale, it's Gaussian fluctuation, right? So you look at large scale, it's Gaussian fluctuation. You look at small scale, it's Gaussian fluctuation. That's what means it's a fractal universe. Is that true? Okay, this is theoretical discussion, right? Is that true observationally? It is true. So that's what here. It's amazing. So here. So this figure is showing a power spectrum. So this is a power, okay, at different, so this is Fourier space, okay? So this is a power spectrum power, and then this is, well, actually this is L, it's spherical, so it's not K, but then it's the same. It's just spherical coordinates, Fourier number, wave number, okay? So this is large scale, and then this is small scale, right? I'm sorry. This is, it's the opposite. This is large scale and this is small scale, right? And then you look at it and then these are data points. And then amount of fluctuation is same, right? It's all Gaussian fluctuation. This is CMB measurement at very large scale. So this is consistent with inflation theory. Isn't it nice that you theory discussed on the table and you look at the data with a telescope and then, oh, it's true. It's Gaussian fluctuation. There's a little bit of deviation. So the black line, so this is dotted line, it's the completely fractal universe, right? As we discussed. But, there's always details. If you consider these details, more realistic case, theoretical projection is this black one. There's a little bit power increase at smaller scale, but the data are consistent with this black line. Okay. this is only looking at a very large scale. In small scale, there's a nonlinear regime come in that we are going to talk about in the next chapter probably. So do you remember that we have a CMB power spectrum has this zigzag, right? We are going to look at in the next, okay, maybe I can just show. Maybe I just show. No. Let's go to next. Okay. So this is typical CMB power spectrum. We are going to look at next chapter. But we are looking at the here. Okay. We are looking at the here and then saying it's almost flat. Because here is affected by nonlinear physics later. So it's not flat anymore because fluctuation is going to be changed later by scattering and then things. So we're looking at the here in the fracture. This part was also Gaussian at the beginning, but now it's changed because of the other physics. Okay. All right. Then, where are we now? Okay. We are still talking about. Where were we? Oh, okay. We are somewhere around here. Okay. And then maybe this name. Maybe you should remember this. No, I'm not even there. Not there yet. Yeah, okay, so this is what we saw. Okay. So we just saw it is constant, right? And then how do we this is a little bit detailed, but how do we take this k, the Fourier wave number? Say if we take it 1 meter inverse or 2 meter inverse with physical unit, then this depends on scale, right? But then universe is expanding, so it's a little inconvenient. So conventionally we use natural log. So K1 is K, and K2 is 2K. Then it's scale independent. It's always we take a log and then so that it doesn't depend on the scale. And then we take this delta log K. It's going to be constant, maybe factor of 2 or something like that. That is more convenient than scale invariant. That's the convention. So we take it like something like this, delta log K over delta sigma square. It's a constant. Then that's convenient to write down this kind of scale independent spectrum. And then this is sometimes called the Harrison-Zeldovich spectrum. This name it's convenient to remember. If you hear Harrison-Zeldovich spectrum, they are talking about this. Okay. Then we call this the fluctuation sigma square. The log K is dimensionless power spectrum. We just intentionally took the log to make it dimensionless. Okay. So now how is this related to a power spectrum? This is just a story that you can see here. But we have Poisson's equation. We have this kind of relation. That's what we often use in physics. And then this is a definition, is delta is fluctuation, delta low density fluctuation over average density. And then Fourier transformation is going to give you this. So this delta is here. So we put it here, and then this is Fourier transformation. And then we can write dimensionless matter power spectrum, which is delta square. It's something like delta k square. So that's proportional to k to the power of 4. Okay? Because from this relation, delta k is, we have k square here, so it's power of 4 here. Okay? This is just converting the equations. Yeah, and then this delta square is dimensionless power spectrum. Okay. Okay. Yes.
Is the delta square here is the power spectrum before the inflection or after the inflection? Because you mentioned in fact for after the inflection, power spectrum is independent to a different scale. So, but here the delta square is relevant to the k as before.
Oh, okay. The evolution is independent of the scale. Okay.
But here the delta square is relevant to the k. Doesn't that mean it is associated with the scale?
No. I mean, what I mean is this k can take different values, right?
Okay.
And then at different values, different k, it's evolve independently.
Okay.
So if k is large, say k and then 2k and then 4k, these evolve independently.
I see.
They are not correlated.
So at the end will become the dimensionless, not dimensionless, the scaleless power spectrum. Does that mean?
Maybe my notation is not very good.
Maybe I misunderstood. You said the delta describe the power spectrum, right?
Yeah.
And in the previous state, we mentioned that the power spectrum after the inflection looks like a flatness line, right?
Right.
So that means the power spectrum is independent to the k. And here, why the delta square is proportional to the k.
Okay, so maybe do I need k here?
So that's
Because power spectrum also, it's a function of k.
Oh, I see.
Maybe I need k here, sorry. It's a little confusing.
So it's not described the whole power spectrum, it is for one independent.
I think so, yes. Yeah, sorry. Okay, then what's next? Next is, am I going to do 3-dimension? Yes, I think so. How many nodes in total? So then in the same way, we just make it 3-dimension. So V equals L cubic, right? And then lambda is L divided by N, and then K wave number is 2 pi N divided by L. Then, N modes in this delta Kx. And then how many modes in total is this times volume. So number of modes in a shell is something like goes like this. This is just derivation. I'm not sure this is input. K appeared here.
Yes.
Then dimensionless power spectrum, this is by definition, and then maybe we put this in here because this part is, I think, this 3 dimension, so we put it here, and then d log k is 1 over k dk, so it's going to come here, and then we have, here's a k square and another k here, so it's actually k cubic pk. Okay. Well, I think it's of course, right, because it's now 3 dimension, so we need 3 here. I think that's intuitive. And then very often we have, this becomes P, power spectrum K, is proportional to K and minus 1. And then, okay. And then this dimensionless power spectrum is going to be K ns plus 3. And then this ns is something called spectral index. Spectral index. This is an important parameter to decide the inflation model. Okay. Okay. Then for completely scale invariant power spectrum, this ns is 1. So if it's 1, this becomes 0 and the pk actually becomes constant, right? Power spectrum constant, as we saw. So if it's completely scale independent, then ns equals 1. So inflation theory predicts this spectral index is close to 1. Okay. But in reality, as we saw in a detailed model, there's a little bit of dependence, right? So a little bit of dependence depends on what kind of inflation models are correct. So a lot of people are trying to investigate, what is this scale number? We know it's close to 1, but is it 1.1 or 1.01 or 1.001? That depends on the inflation model. Okay. Okay. Maybe we can look at this first. Okay, so this is observational result. So this is a current, or this is a little while ago, maybe a few years back, observational constraints on the inflation. So this is ns, the spectral index of the power spectrum. And then this is tensor to scalar ratio. So this I'm going to explain around near the end of the semester. But this is the amount of the primordial gravitational wave. Gravitational wave from the inflation can be detected as a B multiplication of the CMB. And this amount. So this is proof of the inflation theory, so people are trying to detect it. But at the same time, this also primordial, this spectral index people are trying to detect. And then if we look at the constraint, so this Planck plus something is the observation, right? So the tightest one is the blue one, Planck, and then W maperization, and then BAO is in this blue. So the current best estimate is something like 0.96 or so. So it's a little bit deviation from 1. And then, so these are different inflation models, these lines. So some of the lines are ruled out already, and then some of the other inflation models are surviving. Like for example, this dotted line is a power law inflation, which is ruled out already. It's not, it cannot explain the Planck data here. Maybe I don't know. Well, these things are not, which one is this? This one, inflation potential is phi to the cubic, it's up here, so it's also ruled out. This one, inflation potential is proportional to phi. Maybe it's still surviving. So, well, I don't know the details of these models, but this spectral index, by measuring this spectral index, helps to differentiate which one is correct, the inflation model. Okay. And then this, okay, I guess I wanted to, the takeaway from here is this spectral index, this plot you see a lot. This is famous plot in this field. So if you see what is NS spectral index, that is a little deviation in the power spectrum from 1. Okay? If it's 1, it's flat, right? Completely independent. Little dependence is this. Okay? And then that depends on inflation models. Okay? So that's the important things to take away. After four problems of Big Bang. Okay, 4 problems of Big Bang, please, try to take away. Yeah. So in that sense, we are looking at more details this week. So often, maybe, yeah, so inflation can be considered something like that. This is, say, phi is the inflation field, okay? And then B phi is the inflation field potential. And then maybe the universe is somewhere around high in inflation potential, and then it goes down like a gravity this way, and then fluctuate, and then gradually convert this potential energy of inflation to the expansion energy of the universe. And then maybe when this vibration, oscillation stops here, then inflation ends. You can think about something like these are some typical inflation models. The detail depends on each model. Okay. Do you want to look at this detail? Do you want to know this eta and epsilon or no? We're going a little bit more detailed. Okay, maybe this is too much detail. Okay, so let's overview two other key prediction of inflation. So number one is perturbation of matter and radiation should be equal, because at the particle horizon, it's just a quantum fluctuation. It's created for matter, which is gravitation wave, and then radiation, which is photon, in a similar way. So it's adiabatic perturbation. So the matter and radiation should be equal, which is so far okay. We don't see any deviation from this. And then second one is something we look at today. Phases of Fourier are uncorrelated. It doesn't depend on K, and then random to each other. So Gaussian random field. So inflation prediction here, if we summarize, is so the number one is Gaussian random fluctuation. This is what we are talking about today because it's from the quantum fluctuation at any scale. So far, the measurement from the Planck is this 2.5 plus minus 5.7. This is F and L is something called parameter called non-Gaussianity. So how much fluctuation is deviated from Gaussian fluctuation? That's this F and L. And then before the Planck satellite, there are many inflation models with FNL of 100, 200, 1000, something like that. And then, there may be this kind of model, this kind of model. However, Planck made a very precise measurement. The FNL 2.5 plus minus 5.7. This is a very small number, and then this number killed a lot of inflation models that predicts very large deviation from Gaussian fluctuation. This universe seems to be very simple. Fluctuation is just Gaussian, which makes sense, but it's a little boring if you want to think about more special universe. Okay, and then inflation predicts spatial flatness, right? Okay. So in other words, this is boring. I said it's boring, but then we measure the very small non-Gaussianity, which is also, if you think about other way around, this is also consistent with the prediction of inflation. So it's sort of backing up the inflation theory. And then spatial flatness, as we saw, inflation last week, inflation predicts spatial flatness, right? And then we observe very flat universe, which we will see it later in the semester, or maybe next week, next chapter. Okay, and then adiabatic fluctuation is okay. We don't see any deviation from adiabatic fluctuation. Matter fluctuation, and then temperature fluctuation, radiation fluctuation is the same. Both of them are Gaussian. So this is okay. And then the key is here. Inflation predicts gravitational wave background, right? This is what people are looking for by measuring the B mode polarization, which we discuss later in the semester. So these are prediction of inflation, which means if these predictions are correct, inflation theory is correct, right? So this is, these are something to prove inflation theory. And then the last piece is this third one, gravitational wave background through B mode polarization. Okay, so that's that. Yeah, inflation, it's interesting to think. So so generally we think about this kind of inflation, right? This inflation goes down and like this, right? And then at some point in the future, it stops, right? But what if this slope is very shallow? So in this kind of slope, you can imagine, okay, oh, it's going to stop at some point. But what if this is something like this? It's very shallow. And then we're just going down the potential, and then this slope continues very long time. We don't know. No one knows. So if the potential, this is inflation's potential, it's something like this, then inflation might continue forever. We never know. Our universe is maybe only this tiny part, but in the very long future, maybe inflation continues. We never know. It's interesting to think about. So we also look at the minimum time scale that needed for inflation, right? I forgot the number, but what is it? 10 to the minus 33 seconds or something like that. That's a minimum amount of inflation. We at least need that long inflation. But there's no maximum. It's okay inflation to continue 1 year or 10 years or 100 giga years. Yes?
You mean that inflation is going on even in our universe and...
That's possible. That's possible. So, I don't know, it's a little, it's interesting, but for me it's a little bit, irritating that inflation might have continued a long time before us, and it might continue very long time after us. There's we don't know. Before, probably no way to know. Yes?
If the exact energy release from the reflection is like the rolling ball, doesn't that mean the energy release is the oscillation? So why we assume the inflection is only expansion, and there's not like oscillation from your illustration?
That I don't know. Can you look at the inflation theory?
Sure.
That's a detail I don't know.
Okay.
I'm not a theorist, so. But that's a good question. Yeah. So I show you this, right? And then okay. This. So if inflation model is something like this, then we may be able to detect it soon, 0.05. If it's 0.01, probably we can detect in 10 years. But what if this inflation energy scale is 0.000001? We never be able to detect it because there's a limit in quantum fluctuation of our experiment. And then we never know what is the inflation potential. It depends on the Mother Nature, right? If Mother Nature gives us a hint, we can figure it out. But if Mother Nature didn't give us the hint, then we never know what's the inflation potential. well, I feel a little bit, hopeless. There's some limit in human, I think. Like this is the same, right? For dark matter too, right? Dark matter, we know that it's a little very weak interactive some matter. If there's a weak interaction, if there's a little bit of interaction, then we might be able to detect it, right? But what if it's zero interaction? How do we detect it? There's no way, no? It only depends on the nature. I hope, nature give us some hint, just a little bit of interaction, please, so that we can detect it. Otherwise, if it's zero detection, then, yeah. Like a student who never comes to class, right? If you even come to class one time, then I can detect student's face, right? Well, if students never show up in the semester, there's no way to know who is this student. Like, I think humans there's a limit in human capability. Anyway, I think there are a lot of situations where we face this in cosmology, and one of the examples is this inflation theory. That's not much information for now. But okay, never give up. I mean, hopefully, it's somewhere around here. Nature gives a hint, and we can detect, and then we get Nobel Prize. That's the hope. Okay, so this is the end of this chapter. So maybe shall we have a break? Maybe we have 15 minutes break. So please come back at 3:35. 3:35. Okay. Okay. See you at 3:35.